Hi guys, welcome back. So I'm just going to quickly just try and on the fly think up some examples of how pointers work. So to do this, I'm just going to write some simple code. So I've got a very basic CMake project, build, cd build, C, hopefully, and I think there'll be like some hello world or something in here. Yes. So if we run this, bin, where does it get generated to? I'm going to make it first. Bin bar. Yes. Okay. So we have essentially it's just printing hello world and the process ID of this program. But now, so we talked about the stack and the heap and whatnot. So we can, I'm not going to go and break down memory maps of compiled binaries and whatnot, but more so just look at like basic pointers. So we have, essentially I want to cover looking at structures and the different annotations, like the arrow annotation and then the asterisk annotation, variables, and also arrays, because these are sort of when pointers are used. Specifically, like the perfect or the most common array that you'll see is the C string, because C doesn't actually implicitly have string types like Python and Java. It uses char arrays, like arrays of characters with a zero, like a null character on the end. And so like a string exists in memory, and all the operations that use strings, they essentially read characters sequentially in memory, as we know memory is sequential, until it finds this null character, and then that's considered the end of the string, right? But now if we look at like this function, we'll get rid of this stuff, and let's just say we'll look at the most basic example. We want to create an int called a, or we'll call it foo, and then we, like in the little lecture slide, we'll create an int pointer called pfoo, right? And I'll set this equal to the memory address of foo, right? And I should probably give this a value. So we'll say foo equals to 2. So now if we make this and run this, maybe make another one, template bin. We run GDB on this, bar, I think it was called. So now we'll break 7 and run this. Now, if we look at, step over this. Now, if we look at foo, we can see foo is equal to 2. And if we print the memory address of foo, we get this long number. And so this is the actual memory address on my system where foo is being stored, right? So this hopefully won't return. So now if we print pfoo, we will see that it should have the same memory. It's storing the memory address. The value stored in pfoo is this memory address. Now I think, will this work in GDB? Pfoo. No. Anyway. So we can see that we have foo equal to 2. It has a memory address of this, but this address is stored inside of pfoo because pfoo is an integer pointer. This is its type, and I set it equal to the memory address of foo by using this ampersand. Now let's expand on this a bit. If I want to, let's say, we'll increment foo, right? And we'll see what happens. But then we'll also, so this is directly incrementing the variable foo, but now we also have pfoo, which is a pointer to it. So if we want to increment the variable using the pointer, we then have to dereference the pointer, meaning it's essentially telling the computer to go to this memory location and use the variable you find there. And then we can increment the variable once we're there. So to do this, we have to dereference pfoo. So essentially saying, go to this memory location and get me the variable that's there. So we know that there's an integer at this location, but to get the integer, we have to use the dereference. So pfoo, it's the same notation as when you create the integer, essentially, the pointer. So we can use this. So in the brackets, we're saying, go dereference pfoo, and then this here, this brackets, the equivalent of the brackets is the variable at that location, which is foo. So now we've incremented the variable at that location. And so now if we build this and debug this, and if we break at 11, we'll see that foo is equal to 2. the location of foo is equal to this, which is also the same as pfoo's value. But now if we increment foo, we'll see that it's now equal to 3. But if we look at pfoo, it's still the same because the memory, the value is still the same in memory. And if we step through this again, we should be able to print foo now, and foo is at 4 because we've gone to that memory location and we've incremented the value there. Now, if I was to do this, let's say, pfoo++, right? So we'll build this and run this, breaking at 15. Hopefully, wait, 15. Did it crash? Because it should crash, but I don't want it to crash yet. Oh, I know what we can do to save it crashing. What we'll do is we'll create b equals to pfoo++. Won't use +1, we'll go this, right? Now we'll make this, and then we'll run this, and we'll break now at 15. So what we have is we have pfoo, which is still print pfoo, pointing to the location of foo. And if we create b and print b, print I should print integer pointer b. Oh no. Print p. This is the next memory location. We can see here we have this, and so we have 32-bit, we have 8-byte memory. Well, it's an integer, so we're dealing with, in this case, what 8 to C is like 9 A, B, C, 4 bytes, so 32 bits, and this is the incremented address. By using pfoo+1, we're actually incrementing the memory address stored at pfoo. So this should point to the next memory address after foo in memory, which, since it hasn't been allocated, can't be accessed. And so if we were to access this, the system would crash and you get a seg fault, meaning that we're dealing with invalid memory and whatnot, right? So hopefully this makes this clear how you access a pointer and use its value. But now with this whole incrementing memory, what I was saying here, how we're this is actually incrementing the memory address stored in pfoo and saving it to B. How this is useful is that if we have, let's say, we'll have an integer array. So we'll have int foo, like an integer array of, where's my insert? We'll have of 5, and we'll create this to be 1, 2, 3, 4, 5. If we print run this, make you, quit you. Now, if we look at foo is this entire, an array, right? So GDB knows to interpret its entire array. But if we look at the int pointer, if we cast foo to an int pointer, it will return us the memory address. Now, if we, this is probably a bit complex, if we dereference that memory address, we'll get 1, because essentially foo, the array, is just a pointer, and it points to the first element in the array. And then by dereferencing that, we're getting the first element, which is the 1. And so this is useful because an array is sequential in memory. So we have foo is the first, if we dereference foo, we get the first value. If we dereference foo+1, we get the second, we get the third. And that's what the square bracket does. It just dereferences foo plus the index's number of the item in the array, and we have integers, so it's just going to step through memory in integer sizes. Like in this case, it's a 32-bit. So this is why we also, in the last little quick example, we're actually 4 memory addresses further in memory, because we went from 8 to C, which is 4, in hex, 8 to C is 4, 9, A, B, C. So now what we can do is we'll just, for example's sake, to reiterate this, we'll create some int A equals, now we can dereference foo. right? And then we can say, for instance, int b equals, we'll dereference foo plus 1. And so if we run this, and we'll break at, we'll go to 11. Now, if we look at A, we can see A is 1 because we're dereferencing foo, and foo points to the first memory, the first location here, and then we're saving its value into A. Similarly, like if we go and we look at B, we're getting B equals to 2 because foo points to this first one. We're going 1 up in memory and we're dereferencing it. So we're taking the value in memory and hereby taking the 2, right? So this is, and also I was talking about before, like this is with the static and dynamic, because we've got foo5 and we've given it a value, this is statically allocated. When I compile my program, like when I type in make, it knows I have an integer array of length 5, and it has this like 1, 2, 3, 4, 5 stored in it, right? So it's statically allocated, and when I compile my program, it knows it exists and it gets allocated into the appropriate memory region. Similarly, to dynamically allocate it, meaning it'll get allocated when my program is run, I can use like the malloc, calloc, whatever. And so to do this, like malloc, if we look at the manual for it, allocates size bytes and returns a pointer to the allocated memory. And so it's returning a void pointer. So we need to, so this is saying it's returning a pointer to whatever was allocated, and we need to give it the size that's getting allocated in bytes. Now, we want to create the same, we'll keep the other one there so we know, we want to create the same array dynamically. So we need an int pointer because malloc returns the pointer to the array to us. Now we're going to call this one bar, and we want the same thing. We want to have an array in memory of 5 integers. So what we're going to have to do is we're going to have to tell malloc how long we want our array to be. So we want each index to be an integer. So we're going to say size of int. Now this should probably, the size of function will tell us how large an integer is in bytes, and this should be 4. And then we're going to say we want to have 5 of them. So we're going to allocate enough bytes for 5 integers. And so then this is saved in bar. And so similarly, we can access, we should be able, this is sort of like a bit hacky. If we access bar, like if we go, or firstly we'd have to set things, I mean, if we go bar equals 2, bar, second bar equals 3, we would then essentially here have allocated in the bar array this item here. But because we're using malloc, this is just allocating random memory. The contents of bar is completely random, which we can probably see in a second. Make. So, yes. So you see here implicit declaration of malloc, and this is because I don't have the hash. I need to include so I can get linked in standard lib.h. So if I make this now, no warnings, and if I do this, and we'll go down to 13. Now, if I was to print bar, it's a memory location. And if I print bar 0, well, we're lucky, it's 1 or 0. Okay, so they're all been zeroed out. So we're very lucky there. But sometimes this can just be random whatever's in memory. So you don't have any guarantee that what's in memory here is 0 or anything at all. So now we're going to go and run. Well, now we can print bar 2, and we'll see that it's been allocated to 3. Because using the same idea, we actually haven't allocated an array here, but what we're saying by going bar 2 is we're saying go to bar and step +1 +2 along in memory the size of integer. And so it's going to bar, it's going 1 integer size in memory, 2 integer size in memory, and it's setting that memory location, like the variable at the memory location, to 3, right? Now the downside is that this is very easy to allocate and essentially set the memory, but we don't have that luxury using dynamic allocation. So we would have to go through and go bar 0 equals 0, bar 1 equals 1, whatever, right? And then we could eventually set the array to be the same or use something like memcopy. Like we could, using memcopy, it just copies one set of memory to the other. If we look at the manual, memcopy, copies n bytes from memory like area source to memory area destination. And so we can say, oh, I want to populate my bar function with the same contents as foo, so we can go memcopy. Now if we look at it doesn't have the prototype, memcopy, we want the source destination, the source, so the source is foo, the location is bar, and its size of int times 5. So that's how long it is. So if we run this, we need string, because we're using memcopy to get rid of this error, to get rid of this warning. If we run this again and go down to 14, we'll now, if we go to bar like 0, or it'll be 1, print bar 0. What did I do with my n? Run again. Print bar 1. Oh wait, have I done this around the wrong way? Memcopy. Destination source. Okay, so I've got it around the wrong way. So this is my bad. So we need to make this foo, and this is bar. So we're copying from foo into bar. So we'll make this again. Break again at 14. Now if we print bar 0, should see a 1. Okay, so that's dynamic. By doing this here with malloc, we're allocating a chunk of 20 bytes in the heap, and then here we're copying from the foo, like the static variable foo, into this variable, right? So this is just how we use arrays using pointers. Now, when pointers, one last sort of thing that you might commonly come across with pointers is passing a pointer to an entire object. And what I mean by object is like a data structure. So we'll have a struct, my struct here, and let's just put some things in it. Like we'll put a few different variables. So we'll have int a, int b, and then we'll also make an int foo array of length 5 in here as well, right? And so what we can do is we can instantiate this here and go struct my struct, and we'll say this is bar, and we can actually initialize this guy with values. So we can say a equals to 4, dot b equals to 7, and then we can do things like dot c equals 2, and then 1, 2, 3, 4, 5, right? And so this is the annotation to set each member, or should this be a no, I think we're just missing him here. And here we're also, oh sorry, nope, wrong, here. What are you complaining about? Does not have a struct, my struct. Int, sorry, C, no, this is foo. Yeah, there we go. So if we run this, and we break at 20 and go to 20, we can now print bar, and we'll see that it's already been statically allocated. A has been populated to 4, 7 is in B, and then foo's this entire long thing here, right? But generally, this is not what I want. I don't want to cover structures so much now. What I want to deal with is pointers. Now we can also do the same thing again before if we wanted to have struct, if we wanted to make a struct, my struct. If we wanted to dynamically allocate, we'll call it like C, and then we can use malloc to size of struct, my struct, here, and this will allocate a memory, a struct, like it will allocate memory region the size of what this struct requires, and it will return the pointer and save it into C, right? And for instance, here we could use calloc, and so you can look up what calloc is. Essentially, it just allocates and zeroes out memory. So if we can make this, and then we run this and break at 22. If we look at C, you'll see now that we have a pointer, so it's just pointing to a memory address. But if we dereference C, meaning show me what's at this memory address, we'll see that we have a zeroed out structure because we have allocated the size of structure. Now, why I want to get to this, like why I really wanted to show pointers and functions especially, is because passing data into functions that can get modified is very easily done by passing pointers to structures, because structures are very good for logically putting data into chunks, into logical containers, objects, and then by passing in a reference to them, a function can directly modify, like directly access the memory locations, modify the structure, and when the function returns, the modifications are still there. So what we're going to do is we're going to create a little function now. We'll call this, we'll make a void myfunc, and we'll say that it takes in a struct mystruct pointer called this. We'll call this we'll just call this, I don't know, stru. Yeah. And then we have to then pass in a pointer to this structure, and we can do something to it. So let's just say we'll make it really basic. We'll just say stru. Oh, now we get to the fun part. So we want to take stru, and I'll explain in a second what this arrow means, and we'll increment him. So as you can imagine, I'm passing in a structure here, and it has members. And so what I need to do is to access the A, if it was statically allocated, like if I'm in here and I have a statically allocated structure and I want to increment A, I could go bar dot, and then it has the members plus plus. And so this is going to go and get bar, which is my structure here. It's going to take the member, the variable inside of it, the member A, and it's going to increment it. But now we have a pointer. So the problem is that we only have here essentially a memory address. And what we need to do logically is go to that memory address where a structure is stored, go forward in memory until we get to where the A variable is stored, get the value, and then increment the value stored in that memory location by 1, right? And so this dot arrow is essentially this entire process wrapped into a very easy to use thing. But the long process is essentially what we need to do is we need to dereference struct stru. So what we're doing here is we're going to the memory locations pointed to by stru, and then we can go dot, and we can take the member we want, dot A, and we can increment him, right? So by doing this, we're incrementing A plus plus, and then the exact same thing is happening here, but people got sick of doing brackets, asterisks to dereference a structure, dot to access the member. So instead, there's this arrow, and what this arrow does is it dereferences and accesses A of a pointer. So if we pass this in, like now if we want to do this, we'll leave that there. Now if we want to pass in a structure to this function, we have to, for instance, with a statically allocated variable, we need to get the memory address of where this variable is stored. Essentially, we need to create a pointer to this variable and pass that in to the function. To make this really clear, we can make a struct mystruct pointer called pbar, and we'll set this equal to, using the dereference, the ampersand, we'll set this to the memory address of where bar is stored. And then we can call myfunc, and we can just pass in pbar, right? It's because we're passing in the pointer. Similarly, I could have just passed into here pbar, ampersand dereference bar, right? But we're going to put in pbar. And we'll see now if we run this, when I quit this, and we'll break inside of the function. Did I create that breakpoint? Nope. And so now we've passed in, if I look at bar, there's no context. So let's actually restart this and go back to the beginning. So clear 15 and break at 28. So printing bar, we see we have 4, 7, and then we have a little array. We step through it, we've accessed the member. So now if we print bar again, we've incremented A by 1. Now we're going to create our pointer. So if we look at pbar, we have essentially this value, right? So we'll just we have that one there. Now if we step into the function and we print stru, it's the same value, because, and this makes sense, because it's a pointer. All it stores is a memory address. So when myfunc returns, stru will actually get popped off of the stack and it will no longer exist. But it doesn't matter, because all we want from stru is the memory address where we can access our structure. And so by looking at, if we dereference stru, we will see that this is actually our bar structure, because it's going to the memory location where the structure is stored and it's showing us what's there. So if we now run this line of code and we print our stru again, we'll see that we've incremented A again. And the good thing is that now when myfunc returns, this variable stru is destroyed, is popped off of the stack, but the modifications we made in memory, they're still there. So now we're going to go through and use the second annotation, and we'll see that we've incremented it again because these are equivalent, but this one's just a lot easier to write, and you'll see this in your code 99.9% of the time. So now we'll return, and so obviously I don't even think this is possible because we're not in the context, but stru obviously doesn't exist. But if we look at bar, we've still got 7. These 2 incrementations that we've done have happened and they're still valid. And so similarly, if we were to run this line again, but we could then straight up run myfunc on top of C, because C is already a memory pointer. So we can just pass it in. So if we compile this and run this, and we'll want to break at 30, so we'll go to 36 again. So run, and we'll go to here. Now if we look at C, we'll look at C's contents. We zeroed it out, so it's all zeros. Now if we step into this function and increment this, we'll go look at stru. It's now showing us the contents of C because we passed in C's address, and it's incremented the A. So obviously this is going to do the same thing, but now we've returned from myfunc, and if we print the contents of C, we'll see that those 2 incrementations have still happened, right? So I don't really know what else I can do to explain pointers. They're a practice thing. I hope this has helped. It might be really hard to follow. When I first learned pointers, it took me like way longer than I'd be happy to admit to get my head around them. They're a bit tricky, but it's not so much the concept of a pointer, but it really is getting to terms with the syntax, like when to use an ampersand, when to use an asterisk, when do you use the little arrow, and this is just practice. And so I really hope that you guys will figure this out, and they'll help a lot because you're going to need them for the course, because you have this object-oriented stuff, and all of my functions work in this kind of fashion. So thank you for watching. I hope this has helped someone. And I will see you guys in another video.